So is there anything you guys want to talk about with respect to class procedure, old homeworks, new homework? Well, we'll get to the new homeworks later before we finish off homework 7. Is there any old stuff? So I still owe you an exam. It will probably be next week before I grade it. And that's about that. It'll be next week. But again, don't fear. You guys did great. I was really impressed with how you guys did. It was a good day for just about all of you. And the ones that it was not a great day, it was a good day. So do not fear. No old questions? All right, if we have no old questions, my list begins with Christopher and where we left off, which I think was problem 14. Is Chris here? Yep. So one of the many missing. Oh, yeah, there he is.
Yeah, let me just share my screen here. Let's see. I believe that's the right one. Okay, so I essentially just kind of set it up according to how you explained it last week. So you can see we have our essentially, I guess, frequency table here in which we, according to the sort of setup of the problem, specify that, let's see, the B2 alleles are selected 50% of the time. And the, and then in the control cases, they're selected 30% of the time. When you sort of cross tabulate, this is the sort of transformation that you make to each cell. And then you essentially kind of plug into the formula for chi-square, these statistics, and I believe that is so 2n times this times this, or this times this, yep, and this times this squared divided by this times this times this times this. That simplifies out to I gotta take that, chi-square equals n over 12.
That 1.5 is probably supposed to be a 0.15 would be my guess.
Ah, yes.
But otherwise that looks awfully strong to me. So the key things to remember when doing these sort of contingency tables, the thing every student more or less will get wrong at some point in their life is contingency tables have counts in them. They do not have frequencies. So if you include a frequency in your, if you do it on contingency, if you do your contingency tables on frequencies, you will discover that it's insignificant. Always 100% of the time, because it's effectively bound by the number 1. You never get a chi-squared of 8 if your contingency table adds up to 1. So that's the first thing to remember. Everything's on counts, and you can, of course, do it, effectively the way you were taught in, maybe junior high school or whatever, that it's the frequency of the row, the frequency of the column, multiply the row probability by the column probability by the sample size. That'll get you your expected, and then take your observed minus your expected squared, divide by the expected, sum over all the boxes on the table. That will get you the chi-squared, but I promise you'll get the same answer just by going the diagonal, one diagonal, sort of one value in the diagonal times the other value minus the other, that sort of cross product term that we've already seen for a Bernoulli random variable is a covariance. And then your squared covariance, and then when you divide it by all the row sums, you've already seen for Bernoulli random variables, those row sums and column sums are also variances. So what you've done is you found your chi-squared was in fact the covariance between those two random variables squared over all the variances times that. That your standard chi-squared test statistic is effectively a test that the variance explained by the variable is significant. That the squared correlation coefficient between the two variables over all the variances times your sample size is a chi-squared. And as a scientist moving forward, that's how you always want to think about the world. That, is this significant or isn't it? Well, there's maybe a very sophisticated, fancy way of testing, but in your own head, when you're just trying to like wrap your mind around, what do I think is likely? Find the correlation between the things, square it, multiply by the sample size. Is that number bigger than 4, bigger than 10, bigger than 30? It's a number like 30, you're like, yeah, it's going to be really highly significant. If it's a number like in your head you can see is less than 4, you know, there's nothing there. Anything in between, you're talking about doing statistics. And while there may always be more powerful tests, more specific tests, more better, cleaner ways of modeling your data, anything that gives you a qualitatively different answer than take the correlation, square it, multiply it by the sample size, anything that's qualitatively different than that is probably wrong. And it probably means you made a mistake. That the variance explained by the variable you're interested in times the sample size has to be a number at least, you know, like above 1 and above 4 and maybe above 30 before you're going to get really excited about it. Does this make sense to everybody? And we will see this again as we start looking at stuff like population subdivision next time. And again, the associations to disease and stuff. But ultimately, the simplest tests will all come down to a chi-squared test that looks like a covariance that you're testing divided by the variances. Or in other words, the proportion of the variance that is due to the thing you're testing. That's the intuition, that's the specifics. Hey, Kevin, you want to show us the next problem?
So I didn't redo it, unfortunately.
Okay, let's see what you got. And we'll talk through it and then maybe we'll show mine.
Okay, hold on one second. Let me pull up my, let's see. Seven. Okay. All right. Oh, I definitely know this is going to be wrong, but I'll share it anyway. And I think I made the assumption on my first pass that like I had to find, we'll see, you'll see.
Before we go on, can I ask a quick question about that last problem?
Oh yes, sure, please, I'm sorry.
What was the sample size you were supposed to end up getting?
Beats me. I was stupidly non-specific. So the answer is you could have designed that study any way you wanted. The way I designed the study is I had equal numbers of cases and controls, and that was clearly the way Christopher designed it too. Let me show you my screen. And let me, why am I so stupid here? Sorry. Nope, that's not what I wanted. Tech shop. Oh, I can't believe if I've closed it. Let's see. All right, I've managed to close. Oh, no, there it is. All right. So it's at the bottom of the screen here. So the idea is we're supposed to find the sample size measured in in some fashion or other. The first thing I did is I assumed an equal number of cases and controls. There is no reason to have assumed that other than, well, it's often, well, sometimes people have equal numbers of cases and controls. And I called the number of case chromosomes N and the number of control chromosomes N. So 2N is the total number of chromosomes in the sample, or total number of alleles in the sample. So the number of people is probably half that. So the number of people might be N. And the frequency, so therefore the counts in here are something like 0.5N, 0.5N, and so forth. So when you do the sort of simple math, the final chi-squared value you come out with is you find that chi-squared is equal to N over 12. So, well, for your sake, we can call that now a lambda and a non-central chi-squared if you were trying to do a power calculation. So, so right off the bat, you know that you have 50% power to find a chi-squared value bigger than N over 12. If that is the lambda in your non-central chi-squared. So if you were looking for a chi-squared value of 3.84, you'd end up with 92-ish chromosomes or 47 people in cases and 47 controls or something like that. Or if you're looking for a bigger chi-squared, you'd end up with more people. Is that all clear? Taylor?
Yep, thank you.
Yep. So we have not, and we will not in this class talk about power precisely. But if you guys were doing a classical power analysis, the way you do it, at least for chi-squared tests, is you calculate the expected chi-squared value in the alternate model. And the expected chi-squared under the alternate model, like here, the alternate model being association with these probabilities, that expected value is called, was often given the designation lambda. And the distribution of values follows something called a non-central chi-squared with parameter lambda. So you can, from that, look up the probability of getting a chi-squared value, getting a value bigger than or equal to anything you like. And the rough approximation that you should always have in your head is the expected value from the chi-squared test. If you have an expected value of something, that means you'll end up with about 50% power for that statistic. You need a bigger lambda if you're trying for 80 or 90% power. But anyway, who cares? This is just all about rough scales. We're population geneticists, we're not statisticians. Okay, do you want to show what you got, Kevin, or should I just show what mine is?
No, I can show mine. I can
Okay.
show my logic and then tell about how I would do it differently. So
yeah, sounds good.
So I think when I started this problem, I wanted to start from some sort of, well, first of all, this was before you explained all the chi-squared stuff. So
yeah.
So I was trying to derive this X3 by looking at Q1 and P1 and P2 and assuming something about it. Probably assuming that was at equilibrium and that I could figure that out. And plugging in things like X1, X2, or X3 and seeing if I could figure that out. But the way that I would probably go about it now, knowing that I have cases and controls, was looking at those counts and deriving frequencies from those counts. And then going back and figuring out D from that, and then using all this stuff here. And yeah.
That's exactly right. That's what you had to do.
Yeah.
So, so we'll walk through this problem because it's kind of a lengthy problem. And I probably got it right. So so it may sound artificial the way I've phrased it, but this is more or less the null model for how disease works, more or less. That it's really sort of biased sampling. And so if the B2 allele contributes to disease, people who have the B2, who have disease, will have biased resampled from the general population in such a way that their probability of getting a B2 allele is higher. That's sort of the way we think about it, sort of going backwards in time. Going forwards in time, it's like conditional on having a B2 allele. Your probability of being in the disease group is higher. But if you condition on already having disease, you're sort of thinking about it sort of in almost time reversed. So the problem tells you to imagine that well, disease people have the B2 allele probability 50%. And really what it's going to try to figure out is what is the frequency of the A1 and A2 alleles in the population of people with disease and the population of people without disease. So we do that with just Bayes' theorem over and over and over again. The probability of A and B is equal to the probability of A given B times the probability of B, or the probability of A given B is equal to the probability of A and B divided by the probability of B. So we start with working out the conditional probability of A1 in controls. The probability of A1 given B1 in controls is equal to the frequency of A1, B1 haplotypes in controls divided by the frequency of B1 in controls. We were given that haplotype frequency was 0.5. We were given this allele frequency was 0.7, or at least we worked it out last time. So that conditional frequency is 5/7. This conditional frequency is 2/7. This conditional frequency is 2/3. This conditional frequency is 1/3. So these were just the numbers from controls. These were just the numbers given up here. The frequency of the A1 allele, given that you have a B1, is 0.5 divided by 0.5 plus 0.2. The frequency of the A2 allele is equal to 0.2 over 0.2 plus 0.1. Oh, yeah, I've said that right. I may have already confused myself. That might have been the conditional frequency of A2 given B2. Anyway, get it right. So those are the conditional frequencies in controls, but what we want to do is we want to figure out cases. And the problem asks, it tells us that these conditional frequencies will be the same. So the conditional frequency of the frequency of the haplotype A1, B2 in cases will be the conditional frequency of A1, B1 in cases, which is the same as it is in controls, times the frequency of B1 in cases, which is 0.5 by the problem supposition. So it is what we work out here, 5/7 times what the problem tells us. The frequency of B1 is 1/2. So we end up with a frequency of that haplotype being 5/14. We end up with a frequency of this haplotype being 1/7, this one being 1/3, and this one being 1/6. So now we have the frequency of all the haplotypes in controls, which were given to us, and all the frequencies of the haplotypes in cases, which we've just worked out. So we figure, from this, we can now figure out the frequency of the A1 allele, which is the frequency of an A1, B1 haplotype, 5/14, plus the frequency of an A1, B2 haplotype, which is 1/3. And if you add those together, you probably get 29/42. The frequency of A2 is the frequency of an A2, B1 haplotype, 1/7, plus the frequency of an A2, B2 haplotype, which is 1/6. If you put those together, you get 13/42. So now we have the frequency of A1 and A2. To find our usual D statistic, we get the frequency, we get D is equal to the frequency of an A1, B1 haplotype minus the frequency of A1 times the frequency of B1, or the frequency of the haplotype was 5/14. The frequency of A1 in cases is 29/42, which we found here. And the frequency of B1 is 1/2. That works out to be 1/84, 1/84, or some number. Therefore, R squared is equal to 1/84 squared divided by all the allele frequencies. That's equal to 84 squared. It all cancels, and you just get 29/13. Does 29 times 13/1. Does anyone want me to step through this slower or talk about any particular step?
I have a question about why you use Bayes theorem in that way. Like, I guess what necessitates that? Like, what part of the asking that question necessitated that
Well,
conditional?
it's really the part of the question that said you get the haplotypes in cases by biasly sampling controls.
Mm.
So by doing that, I'm forcing the rate at which I get an A1 allele to conditional on the B allele to be the same. Because what I'm saying is I'm grabbing a B2 allele and I'm not looking at A in any way. So when I grab the B2 allele, the frequency of the A alleles, given I got a particular B2 allele, a particular B allele, say the B2 allele, has to be the same as it was in the control population. There's nothing about that process did anything to the A1 or A2 frequency. So by making my cases be a sampling of the controls, I'm requiring the conditional frequencies of the non-picked alleles to be the same.
Yeah.
And then once you say, that's what I did, I made the conditional frequencies the same. If you just look at the ratios, you might actually guess everything right if you got the right intuition. But if you don't have the right intuition, just plow through the Bayes theorem over and over and over again. It is probably easier to plow through the Bayes theorem than always get it right intuitively. But many of you may have gotten it right intuitively, just looking at making sure the ratios are the same.
Yeah, I think I got close values because I think the way that I approached it was sort of similar to what Kevin had done. And I may have built a contingency table without actually building a contingency table and then kind of going from there. But I basically use the values of P and Q to then find the values of X1, X2, X3, X4. So the different haplotype frequencies, I guess, or the different.
Yeah. So if you assumed the R squared in cases was going to be the same as the R squared in controls, they aren't exactly the same, but they're close. You could probably work out an approximation to the allele frequencies just from the R squareds, if that makes sense.
I think so. Can I show you what I did?
So to remind ourselves before you do, so when we calculated R squared in controls, we got 0.2267. And when we calculated it in cases, we got 0.0265, something like that. Is that right? They're a little bit different. They're very, very slightly different. 2267 in controls and 265. So they differ by 15%. This is not a very, very big difference. But anyway, so show me what you got now.
Sure, yeah, because it's weird because I think I got similar values for like all these frequencies, but not so much for the R squared and the D. So 1 second. Okay, apologies for it being a little bit faded, but so basically how I had set it up was I had the changes in the frequencies. And I had set it up so I had my P values. I knew what my Q values were. This is what I knew that I needed to solve for was the X2 and the X4 because those are the two different, not heterozygotes, but A and B, A1, B2, A2, whatever. So then I think what I just ended up doing was solving for X2 and then using that to help me solve for X4. And it gives you pretty close values. So I think with Bayes approximation, it's something like 2 point, like when you break down the fraction, it's like 0.2 something, and this is like point, I forget, but they're pretty close. So I don't really know why, but again, then when I solve for D, plugging in what I knew of the values seems to be pretty off.
I think you just got a calculator error there. That is probably fine. I think. Maybe. So you got a number that looks like, yeah, 2% on the top, and you've got a number that looks like 0.2 times 0.1. Oh yeah, well, that is peculiar, isn't it? Something went funky here, I think. So something went funky here in your estimates of the other two haplotypes. You easily could do this by assuming the R squared is the same. You should be able to find the other two haplotype frequencies, given the allele frequencies. You have enough data to do it. But something must have gone wrong in the algebra here. So my guess is so Gillespie called X1, X2, X3, and X4 the haplotype frequencies. My guess is we've used them as an allele frequency somewhere accidentally.
Oh, okay.
And
Maybe that is the problem. Or maybe that's what I had done. Maybe I plugged something in down here.
Yeah.
Looking.
Yeah. It may have gone wrong here, but that idea could have worked.
Okay.
That by forcing the LD to be the same, we could have worked out what the other two allele frequencies had to be.
Okay. Yeah. Yeah, I think like if you actually rearrange some of this into a box, you could actually kind of do the conversions as if you were changing the sampling, but it just doesn't, it's not in a box.
Yeah. Other questions? Anything anyone else wants to sort of talk about, think about? All right, up next is Zhangji with the next problem, whatever that was. Did we make it through?
Yeah. So I should be sharing the correct screen now.
Yeah.
Okay. So I'm just using a heuristic argument instead of computing the solutions for 14.
Yeah.
So if I have two loci A and B, maybe I should draw this instead.
Yep.
Maybe that would make more sense. So if I have two loci A and B, and I know that the A locus is associated with the disease, but I'm not able to sample A directly, but I know that A is linked with B. Then if I can, I guess, compute the D statistics or the linkage disequilibrium for locus B, then I can also perform the same chi-square test or the approximation to the chi-square test to test for association between the B allele and the disease.
Yeah. Yes, this is absolutely correct. This is absolutely what I wanted you to learn from this problem, and I'll show it to you. This is 100% correct.
Okay.
Let me convince you that that is true, though. So, that is in fact what we were intended to learn from this problem. So let's figure out how to share my screen again. So this is the bit that we wanted you to learn. So in the previous problem, I worked out, among other things, the frequency of the A1 and A2 alleles in cases. And the problem, and we've assumed we know what the frequency of the A1 and A2 allele is in controls. The problem says in controls, the frequency of the A1 allele is 7/10, 0.7. The frequency of the A2 allele in controls is 0.3, 3/10. We worked out in problem 15 that the frequency of the A1 allele was 29/42 in cases, and the frequency of the A2 allele was 13/42 in cases. Again, I assume an equal number of cases and controls for no good reason other than I felt like assuming it. Makes my math a lot easier. So again, the simplest test for association is the chi-squared test. I take this thing times that, this thing times that, I subtract them. I then square that, that's my covariance term. I take all the terms on the bottom, those are my variance terms. I end up with something that looks like sample size times a covariance over all the variances. I'm doing this in terms of a general n. I've pulled out, you notice this is an n squared, this is an n squared, so I pull it out as an n fourth, this becomes an n to the fifth. I got a bunch of n's on the bottom. I end up with 2n times something on the top with a whole bunch of other numbers on the bottom. And I get this chi-squared value is equal to my sample size times a little bitty number. And what I wanted you to learn from this is exactly what Jiangxi already knew. And I think Taylor mentioned it too. When she did it originally, she just assumed the result as well. That if you type the disease that's true, the thing that is truly causative. So here, the B2 allele is contributing to disease, and it has some effect. And I get a chi-squared value from testing the B2 allele. The chi-squared value I get turns out to be my sample size over 12. If I don't test the B2 allele, I don't test the thing that is directly causative of disease, but instead test something else, the chi-squared value I get from testing something else other than the disease allele turns out to be roughly the chi-squared value at the disease allele times r squared between the disease causing thing and what I tested. So it might not be quite obvious to you until you plug in numbers, but this chi-squared turned out to be n/12. This chi-squared turned out to be n times a lot of zeros and a 2. And the r squared between them turned out to be 0.0265. 0.0265 divided by 12 is really, really, really close to this number. Like they differ by like 3%. And if you'd used the chi-squared in the general population, you would have gotten the right answer or in controls, you would have gotten the right answer up to, like 14% error. But I was making you do this to go through to sort of plow through the math yourself, and then be shocked in the end that test statistics are kind of transitive. I mean, not exactly, but they kind of are, and at least approximately in your mind. So if you test one thing, you get one value. Test another thing, you get another value. If this were positive and this weren't, the value you get at the other thing is decremented by the proportion of the variance explained by their relationship to each other, by the r squared. The r squared between them is really giving you the sense for how much power you're going to lose by testing not the thing that causes disease, but something else nearby, say. And it is the reason that when you say, if you're a geneticist looking to do disease association studies, it is the reason you're trying to create a set of markers around the genome such that all of them have roughly largish R squareds to almost everything else in the genome. The reason you're picking like genome-wide markers, like 1 million of them, is because it'll turn out, at least in humans, that at about the scale of 1 million markers, the vast majority of high-frequency sites have R squared to something type that's large when you have about 1 million markers. It just turned out that way. But this is your deep, intuitive understanding that if you don't type a disease allele, but type something different, your power at the other thing looks like the R squared to the disease allele times your power at the disease allele. Is this all clear to everybody? So you should do your best to onboard this understanding. And it will inform your intuitions for the rest of your life if you're doing some mapping experiment for whether or not you think you have enough markers. You got enough markers when you have reason to believe you have a high probability of having a large R squared to most everything in the genome. When you don't have that, or at least to the thing you're trying to find, when you don't have that, you maybe need more markers. Questions? Okay.
So
Yep.
Sorry, I do have a question. Conceptually, so in this instance, so if we have two loci, we're looking at a loci, we're testing the loci that isn't the diseased allele. We kind of have to make the assumption, right, that they're independent of each other, right, in order to see that. No?
No, they are, in fact, they are correlated with each other with an R squared of just a little bit.
Oh, okay, so then yeah. So if we sample the not diseased allele and they're correlated, I guess I'm still like a little confused why they could.
Why would they be correlated? Because they're physically near each other.
Right, yeah. So, because I know that goes into like ideas about hitchhiking, which I think we're going to be talking about, but
yeah.
I think
so things that are nearby each other that haven't had a lot of time to combine between each other might have large linkages equilibrium.
Okay.
Things that are far away from each other or have had a lot of recombination between them will necessarily have small amounts of linkage disequilibrium.
Okay. Cool. Thanks.
Other questions?
I wanted to ask, so when people do GWAS studies, usually they have to control for false discovery rate because they're testing so many alleles. So
yes, that's usually why, like, you've heard the word chi-squared of 30 out of my mouth several times. And that's because a chi-squared of 30 has a probability of 10 to the minus 9-ish. So there are maybe 3 billion bases in the genome. Almost any way in which you try to control for false positives will suggest a threshold that is probably on the order of 10 to the minus 9th or not quite there. Maybe 10 to the minus 8th, maybe 5 times 10 to the minus 8th, but somewhere in that range. So you know if you've gotten the p-value of 10 to the minus 9th, you've probably successfully controlled for it without trying very hard or thinking very hard. But in general, we might imagine being very precise in our model of trying to estimate what fraction of our associations are statistically significant, conditional on the amount of tests we've done, and conditional on, say, the structure of how the tests are related to one You're probably not going to solve that problem unless you do a permutation, but you might be able to approximate it if you use something about the, say, matrices of R squared values between every test statistic. You can probably approximate that very well, getting an estimate of the number of independent tests you did. And from that, you can set up a false discovery rate in a standard Benjamini kind of way. But we're not going to really talk about statistical significance in here per se, but it should be intuitive to you guys that if you do 1,000 tests, getting a p-value of 10 to the minus third is not surprising. If you do 1,000,000 tests, getting a p-value of 10 to the minus sixth is not surprising. If you do 1,000,000,000 tests, getting a p-value of 10 to the minus ninth is not surprising. So whenever you do anything on genome-wide scales, if you start testing millions to billions of things, you better be thinking p-values in the tiny, 1 in a billion range or less. Questions? Next week, we will also talk about how population substructure can mess with genome-wide association tests. And we will, in fact, prove the manner in which it does. But we're still on this week, and we're still on Julie talking about problem 17, unless somebody else has questions.
Sure. Oh, so the question is about what is meant by the term genetic hitchhiking. So I wrote that when a new advantageous mutation sweeps through the population to fixation, alleles that are closely linked in position to that locus will increase together as well. And then this increase in those loci is called hitchhiking. And then, so since they're close in position and then they don't have much chance to recombine, genetic variation in these close locations will be reduced or eliminated so that they would have a low recombination rate.
That's it. And therefore the result of this is in regions that have very low recombination rates in the genome, those regions tend to have lower amounts of variation in the rest of the genome. So if you go scan along the genome and find a region with a very low recombination rate, you almost always find that it has very little variation. In flies, there is not so much recombination in the telomeres or centromeres, and as a result, there's very little variation in the telomeres and centromeres. In humans, there's very little recombination in the centromeres, and therefore there's very little variation found. But right near the telomeres, there's often a lot of recombination. So there's a less sort of profound reduction of variation at the tips of human chromosomes. But this is just right, that if selection pulls alleles around, neighboring neutral alleles will change in frequency too, with the average heterozygosity at the neighboring neutral allele being lower than it would have been in the absence of neighboring selection. And when the selective force is positive, we call this phenomenon genetic hitchhiking. For whatever reason, when the selective force is negative, reducing an allele frequency, we call it background selection. They have much in common. some differences. But at the effect at the neutral site is very similar for both, which is the amount of heterozygosity at the neutral site is reduced relative to what it would have been had the neutral site not been near a site that was under selection. The fixation rate at the neutral site is exactly the same as it would have been if it had been anywhere else in the chromosome. So the rate of evolution of neutral sites, the rate of substitution of neutral sites is unchanged, but the amount of variation, the heterozygosity of neutral sites is reduced by late selection. Questions? And lastly, let's get to Linnea with John's last contribution before he retires.
Okay. All right, so question 18, what is genetic draft and how could it solve the heterozygosity problem tackled by IOTA? Roughly what fraction of substitutions need to be positively selected? So I guess genetic draft is just the term that they used for hitchhiking as an evolutionary force. It wasn't super clear to me what the difference between draft and hitchhiking is. But they said they call it draft because it's somewhat like drift in that it resembles it in like its moments, like its expectations, and I think it's variance if you scale the population size by something. And also like drift, it decreases the heterozygosity. However, unlike drift, genetic draft will, when n gets large, actually asymptote the heterozygosity to a certain value. That's a function of the mutation rate. So Gillespie suggests that this could provide some explanation for the problem that was faced earlier, where they saw that the levels of variation between populations with different population sizes was remarkably similar. So if this variation was controlled by a draft instead of drift, that could be a potential explanation for that.
So in about how many, at least for fly-like numbers, do you have a sense for what fraction of fixations need to be advantageous to get to the sort of asymptotic part of the curve?
Yeah, they did the calculation for Drosophila, and they said it was 1 in every 100 substitutions.
Yeah, everything. Yeah, that's just exactly right. So so this is a little bit of a history lesson here. So genetic drift, hitchhiking. What hitchhiking does to heterozygosity was first derived in like 1974 by Maynard Smith, and then in the early 80s, Chuck Langley and his group had a whole series of papers, sort of basically elaborating on a lot of Maynard Smith's basic results, largely through simulation, but occasionally through a little bit of calculation. But it was more simulation than anything. Anyway, so eventually, right before he retires, John decides to look at the problem of what does genetic hitchhiking do when hitchhiking is recurrent, when you get not a single site coming through, but one site after another, after another, after another, at some rate. And it turns out the problem is fully solvable analytically, at least approximately. And what John shows is that it doesn't take a large fraction of alleles being selected positively and going to fixation due to positive selection for heterozygosity to be fundamentally nearly independent of population size. And this is John's in most of our explanations for why kind of sort of every organism has about the same levels of heterozygosity, because natural selection exists. By the way, this argument also sort of works with negative S. So if there is constant selection, both for positive and or negative allele, so if mutation is constantly creating alleles that are under selection, either positive or negative, it will result in a loss of variation from the neutral model. And it will generally, if there's enough of these alleles that are selected, have the effect that the general amount of heterozygosity is only very weakly dependent on sample size, on population size. So that in all likelihood, the real reason almost every organism has almost the same level of heterozygosity at the nucleotide level is that natural selection exists everywhere. And it's probably not that all populations are cycling the way Ney thinks, and we're all hitting the same ice age, and it's leading to a harmonic mean size that's the same for everything. Perhaps a more simple explanation is that natural selection exists, and some small fraction of sites are under relatively strong selection, maybe 1%. A number that also conforms to your knowledge about what fraction of genomes tends to be deeply alignable between species that are very far apart from one another. Tends to be on the order of 1% or 2 or 3 or 5. Not 90, not 0, which might suggest 1, 2, 5% of the genome is under some sort of strong selection. Questions about this? Okay. That will end our discussion of natural selection for now. Mostly end our discussion of natural selection for the term. Next week, we're going to do stuff about population structure, inbreeding, selfing, that kind of stuff. And then we're going to do the relationship between population structure and apparent linkage disequilibrium, which is not caused by the sites being near each other, but actually by population structure. And you'll end up finding results that are remarkably similar to this week's results, even for sites that are not near each other in the genome, if there is sufficient population structure. And you will find that population structure induces covariance between unlinked markers. And that's what you're going to learn next week. The week after that begins quantitative genetics. Your quantitative genetics homework, the first one, homework 9, is long. It is long and hard. But when you are done with that, you will have derived Fisher 1918, perhaps the most important paper in population genetics. It is the paper that explains how Mendelian segregating loci give rise to phenotypes and give rise to the resemblance between relatives. You will go from, I know how Hardy-Weinberg works, to I can predict how much relatives ought to resemble each other. And that's a big, big go. And we're going to walk you through all those sort of derivation. Many of the problems will seem, much like we did when we started selection, will seem almost troll-like in how easy they are. But we're just building one little result after one little result after one little result after one little result until we get to the covariance between relatives looks like R2VD plus RVA. And you will get there in the end through tiny little steps that mostly don't necessarily make sense until you start getting towards the end of the problem. But by the end of the problem, words like heritability, words like covariance between relatives, resemblance between relatives, all that will be crystal clear in your mind. Questions? So be prepared for homework 9 taking you longer than you had otherwise expected. Homework 8 is just normal homework. Maybe even a short one.
Can I ask a question about homework 8?
Yeah. Oh yeah, let's talk about homework 8. If you're starting it, let's talk about various questions if you have. Yep.
Yeah, I mean, I haven't gotten too deep into it, but I just was looking at number 6 and just wondering if we were getting at. So we're looking at two. I think it's number 6. Hold on.
Yep.
Yeah, we're looking at 2 different populations and making calculations separately. But when we are interpreting the result, we're not like trying to. We're just kind of seeing side by side how they compare. We're not. There isn't like a measure that we need to.
Yeah.
Okay.
So let's give you a where's my that's homework 8. You can actually see a typo in my problem 6 that I'm about to fix. Problem 6. This is. Oh, I don't see a typo. There it is. Duh. 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 All right. Share screen. So homework 6 talks about 2 different populations, which at the moment we're going to call population 1 and population 2. They both have alleles at the A locus and the B locus, and they both have the same alleles, A1 and A2. Oh, am I not
sorry? I'm not really sure what you're showing us right now, but it looks like a lot of. It's the answer console. I think we're seeing.
Oh,
which is.
Let's try it again. Can you? Let's try this. Can you see it now?
Yep, now I can.
Okay.
Thanks.
So the problem tells you what the frequency is of A1 and B1 in one population, what the frequency of A1 and B1 is in the other population, and it tells you what the frequency of the A1, B1 gamete is in one population and the other population. And when Brooke did this, she thought I was trolling her because, God, it just looks like D is 0, R squared is 0. In the second population, D is 0, R squared is 0. There is no linkage disequilibrium going on in population 1. There's no linkage disequilibrium going on in population 2. I can apply definitions that involve a half. When I do the arithmetic with numbers like a half, I get a quarter minus a half is a 0. It's all stupid. There's no disequilibrium. There's no nothing going on. That was just the point I wanted you to say. Plug the numbers in. Show yourself, convince yourself that D is fundamentally 0 everywhere you look at it. Look at it in population 1, these things are unlinked. Look at it in population 2, these things are unlinked. There is no evidence whatsoever for association between the A and B locus. Not even a hint of it. These things are dead, flat 0. Nothing. The problem is as stupid and as easy and as instantaneous as you think it is. D is 0 everywhere. Okay? We have done that because what we're going to do is for the next, really the rest of the homework, I think, is talk about a mixture of these 2 populations, where I create a new population. I don't think I ever name it, but let's call it population 3, where half the alleles come from population 1 and half the alleles come from population 2. And for everything that follows, we'll be doing calculations in population 3. And all sorts of shit's going to be true in population 3 that was not true in population 1 and 2. The first thing I'm going to have you do is just measure, standard statistics about population 3. What is the average? What is the frequency of the A1 allele? What's the frequency of the B1 allele? What is the frequency of the A2 allele? What's the frequency of the B2 allele? What's the variance? Variance? What is the variance in the frequency of the A1 allele? And by that, I mean, what is the variance in A1 due to it being sampled from 2 different places? You're getting a sample of 50% from one population and a sample of 25% from the other. What is the variance in that allele frequency, given you have a 50-50 mixture, one of which is 50%, the other which is 25%? What is the variance in the frequency that is due to this, structure? That variance in frequency will turn out to matter and be relatable to a whole lot of other things. If it all goes well for you, you will find stuff like you've got measures of variance, that you have this thing called FST that you'll be able to interpret in some fashion or another. You can start talking about things like the covariance between the allele frequencies due to this substructure. You'll find that covariance in allele frequencies, well, is of course just your D statistic, and these things are not 0. And because of substructure, you will see covariances between the alleles. And you will discover that because there's covariance between the alleles, if this week had been like, if next week were like this week and you've done some test for association, you would start finding significant results even at loci that are physically unlinked when you're in a mixture population. That's the problem of substructure in association studies. And anyway, you'll go through and do all these calculations, and then you'll actually prove that the ratio, that the covariance or the correlations between these unlinked markers is proportional to the amount of variance in allele frequency due to the mixtures. Not shocking once you start thinking about it, but you'll prove all that. But that's where we're going with it. So you started with the problem that looked like a troll that you didn't think could have been that easy, but you were there to establish in your mind that these loci are not related to one another. But when you put them in a mixture together, they start looking related. In a mixture, every site in the genome starts getting mildly correlated with each other. And if you're attempting to find genes that are associated with phenotypes, you have to deal with the fact that in real humans or real animals of your liking, there's a good chance that what you're looking at is individuals who have ancestries from slightly different populations, which induces a covariant structure between all the alleles in the genome. And you have to deal with that if you're trying to estimate an effect at a particular place in the genome. Otherwise, you'll sort of convolve it with every other site in the genome because of the very mild sort of substructure likely in your population.
This might be kind of maybe too theoretical or too heady of a question, but if we're thinking about like trying to divide out 2 different populations and we're seeing a change really when you start mixing populations, the definition of a population is really dependent on what you as the observer is trying to understand, right? So I guess like, because is the if we're looking at 2 human populations, you could be zooming in on like a town and then you sample from 2 different towns and then
Yep.
I guess
Yep.
I wonder like how if these kinds of calculations sort of help you figure out just how different populations are, or if you as the scientist really are making other assumptions or definitions that are helping you then
Yeah.
subdivide your populations to understand how they're related.
Yeah. So to a first approximation, everything you said is right. That the term population doesn't mean anything other than the collection of people I'm talking about. to a first, and if I assume the collection of people I'm talking about have been interbreeding with each other and no one else since the beginning of time, I can apply almost every single result we've seen in this class. But if it turns out that these group of people have not just been interbreeding with each other since the beginning of time, but with other individuals from nearby or not so nearby or far flung across the world, I may have to deal with that depending on what I'm trying to ask and answer. And the reason you will find that, say, most association studies of your favorite disease in humans tends to occur in people whose ancestors come from a single continent is a weak attempt to deal with this problem, just by making the individuals less likely to have really diverse ancestries. But it's only a very weak attempt to deal with it. You'll probably find that if you're going to be serious in the field, you need to be a lot more serious than trying to find people whose ancestors came from one place. But you will find attempts in the literature to do that. And to what extent the differences in ancestry matter will have a lot to do with what proportion of the variance in allele frequencies is attributable to differences in things around the world. That will have a measure called FST. And whether or not you need to deal with it will depend very much on your question, I think. For the human geneticists, they'll be constantly dealing with it. They won't get anything published ever in their life unless they have some explicit dealing with it. Other questions? Okay. So next week should resemble this week, and many of the techniques you use this week will answer the questions for next week. And again, you're going to get covariances and variances in R-squareds almost being transitive. For the very last problem, if you're going to do the proof, you're going to have to know that a correlation coefficient, covariance divided by the square root of the variance, or the squared correlation coefficient, the covariance squared over the two variances, is bounded between 0 and 1. That all correlations are bounded between -1 and 1. All squared correlation coefficients are bounded between 0 and 1. We could prove it. It's a bit of an ugly-ish proof. It's not too super hard. But chances are you've probably run into that already in your life, that a correlation coefficient is between -1 and 1. A correlation coefficient is, or a squared correlation coefficient is between 0 and 1. If you know the correlation coefficient is always less than 1, the proof in problem 12 is really actually shockingly simple. Like instantaneously simple, almost. But it's a deep result that LD between unlinked markers looks like the proportion of variance due to substructure at the individual markers. Questions? All right, enjoy homework 8. Hopefully someday I'll give you your exam back. and homework. Gear up. Make some time in your calendar to do homework 9. It is the homework that will, if you do it right, will have you understanding quantitative genetics the rest of your life in a very sort of intuitive way. And if you don't get through homework 9, words like heritability and additive variance and dominance variance, all those things will remain weirdly mysterious the rest of your life. You'll have like some I kind of get, if you do the homework and do it right, all of this will be crystal clear the rest of your life. And it's probably worth it. Carve out some time and do it right. Questions? See you guys Tuesday.